All right, let's explore. Number 10, the matter-antimatter asymmetry problem. In the first fraction of a second after the Big Bang, the universe did something that should have guaranteed its own immediate destruction. It created matter and antimatter in equal amounts, and those two opposites should have found each other, annihilated completely, and left behind nothing but a thin wash of radiation drifting through an otherwise empty void. We should not be here. The stars should not be here. Nothing should. The laws of physics, as we understand them, are remarkably clear on this point. When a particle of matter meets its antimatter counterpart, both are destroyed instantly, releasing pure energy in the form of gamma rays. For every particle of matter produced in the Big Bang, an equal particle of antimatter should have been produced alongside it. The standard model of particle physics, which is the most precisely tested theoretical framework in the history of science, predicts that this symmetry should have held perfectly. But it didn't. Somehow, for every billion antimatter particles that existed in those first moments, there were 1,000,000,001 particles of matter. That tiny asymmetry, roughly 1 part in a billion, is what produced every atom in the observable universe. Every galaxy, every star, every planet, every human being is the residue of that fractional imbalance. The technical name for this discrepancy is baryon asymmetry, and it remains one of the most consequential unsolved problems in all of physics. Experiments at CERN's Large Hadron Collider and at the Bell 2 detector in Japan have been searching for the source of this imbalance for decades. The standard model does predict a symmetry violation, a phenomenon called CP violation, but the amount it predicts is far too small by a factor of roughly 10 billion to account for the matter we actually observe. Something created this asymmetry. Physics cannot yet say what. We exist because of a cosmic accounting error so small it barely registered, yet so consequential it produced everything. No equation currently written by human hands can explain why the ledger came out one entry short on the side of nothing. Number 9, the flatness problem. When cosmologists measure the overall geometry of the universe, whether it curves back on itself like the surface of a sphere, bends outward like a saddle, or lies perfectly flat like an infinite plane, they arrive at an answer that should strike every physicist as immediately suspicious. The universe is flat. Not approximately flat. Not mostly flat. Flat to within a measurement precision that the Planck satellite, after years of observing the cosmic microwave background, confirmed to be within 1 part in roughly 100,000. That sounds like a satisfying result until you understand what flatness actually requires. In the standard Big Bang model, perfect flatness is not a stable state. It is an unstable equilibrium, like balancing a sharpened pencil vertically on its tip. Any tiny deviation from perfect flatness in the early universe would have been catastrophically amplified over time. A universe slightly too dense would have collapsed back on itself within seconds. One slightly too sparse would have expanded so rapidly that gravity could never have pulled any matter together at all. For the universe to be as flat as we measure it today, physicists Robert Dicke and P.J.E. Peebles calculated in 1979 that the energy density of the universe at 1 second after the Big Bang must have matched the critical threshold to within 1 part in 10 quadrillion. That is a 15-digit precision. In a universe supposedly governed by random initial conditions, that precision is not merely unlikely. It is, by any reasonable statistical standard, impossible. The leading explanation is cosmic inflation, a period of exponential expansion in the universe's first 10 to the minus 32 seconds, proposed by MIT physicist Alan Guth in 1981. Inflation would have smoothed any geometric irregularities flat the way stretching a wrinkled sheet smooths the wrinkles, but direct observational evidence for inflation has never been confirmed. The BICEP 2 experiment in 2014 announced it had found that evidence, only for the results to be attributed to galactic dust. Something set the geometry of the universe with a precision no random process can account for, and the mechanism that supposedly explains it remains, To this day, unproven. Number 8. The horizon problem. Face north and look at the night sky. Now, turn around and face south. The light reaching your eyes from those two opposite directions has traveled for nearly 13.8 billion years to find you, originating from regions of the universe separated from each other by 93 billion light years. Those two regions have never been in contact. No signal, no particle, no influence of any kind has ever passed between them, because the universe has not existed long enough for anything traveling at the speed of light to make that crossing. Yet those two regions of the sky are identical in temperature, measured by the Planck satellite at precisely 2.725 Kelvin to within 1 part in 100,000. This is not a minor curiosity. In physics, two regions reach the same temperature through a process called thermal equilibration, the exchange of energy until both sides balance out. A cup of hot coffee cools to room temperature because heat transfers between the coffee and the surrounding air until they match. Two regions that have never exchanged anything cannot equilibrate. They have no mechanism for arriving at the same answer. Yet the entire observable universe in every direction gives the same answer. The cosmic microwave background, first detected by Arno Penzias and Robert Wilson in 1965, an achievement that earned them the 1978 Nobel Prize in Physics, is the afterglow of the Big Bang itself. Its extraordinary uniformity across the entire sky was what Charles Misner formally identified as the horizon problem in 1969. It means that the universe was born already coordinated, already synchronized across distances that make synchronization physically impossible under every rule we know. Cosmic inflation, Guth's same proposed solution to the flatness problem, offers an answer here too. If the universe expanded from a region so tiny that all of it was already in thermal contact before the expansion began, the uniformity is inherited rather than achieved. But without confirmed evidence for inflation, this remains a hypothesis built on top of a mystery. The universe emerged from its birth uniform across the entirety of space, perfectly synchronized, as if following instructions that physics has not yet found the source of. Number 7. The cosmological constant problem. In 1917, Albert Einstein introduced a term into his equations of general relativity called the cosmological constant. He added it specifically to keep the universe static, because his equations otherwise predicted expansion. When Edwin Hubble confirmed in 1929 that the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder. Decades later, in 1998, astronomers discovered that the universe wasn't merely expanding, but accelerating, and suddenly the cosmological constant was back, reborn as the mathematical placeholder for whatever force was driving that acceleration. Then the physicists ran the numbers. What they found was the most catastrophic disagreement between theory and observation in the entire history of science. Quantum field theory, the branch of physics that describes subatomic particles and forces, makes a very clear prediction about the energy density of empty space. According to quantum mechanics, the vacuum is not actually empty. It seethes with virtual particles, flickering in and out of existence, and this activity gives the vacuum a specific energy. When physicists calculate what that energy should be, the answer they get is approximately 10 to the power of 120 times larger than what astronomical observations show the cosmological constant to actually be. That gap, 120 orders of magnitude, is a number so large it dissolves any intuitive sense of scale. The entire observable universe contains roughly 10 to the power of 80 atoms. The disagreement between quantum mechanics and cosmological observation is larger than that by 40 powers of 10. Nobel laureate Steven Weinberg laid out this crisis with devastating clarity in a landmark 1989 paper in Reviews of Modern Physics, and it has not been resolved in the decades since. If the vacuum energy were anything close to what quantum mechanics predicts, the universe would have expanded so violently after the Big Bang that no structure, no galaxies, no stars, no atoms could ever have formed. Something is reducing the vacuum energy to almost exactly zero and keeping it there with a precision that has no physical explanation. Our two greatest theories of reality, quantum mechanics and general relativity, look at the same piece of empty space and disagree by a factor larger than the number of atoms in the universe. Number 6. The low entropy origin. In 2004, Oxford mathematician and physicist Roger Penrose sat down to calculate how probable it was that the Big Bang would produce a universe ordered enough for life to exist. The answer he published in his book, The Road to Reality, was not a small number. It was not an astronomically small number. It was a number so vanishingly improbable that writing it out would require more zeros than there are atoms in the observable universe. The probability of our universe's initial conditions arising by chance is 1 in 10, raised to the power of 10, raised to the power of 123. To understand why this matters, you need to understand entropy. The second law of thermodynamics states that closed systems naturally move from ordered states to disordered ones, from low entropy to high entropy. Ice melts, smoke spreads, broken cups do not reassemble. For entropy to have been increasing since the Big Bang, which it demonstrably has, the universe must have begun in an extraordinarily low entropy, highly ordered state. The lower that starting entropy, the more improbable the starting configuration. Penrose's calculation reveals just how improbable our starting configuration was. The observable universe contains approximately 10 to the 80 atoms. Penrose's number makes that figure look enormous by comparison in the wrong direction. The number of possible configurations of the early universe that would not produce the ordered cosmos we observe dwarfs our universe's atomic count by an unimaginable margin. Crucially, inflation does not resolve this problem. In fact, Penrose himself has argued that inflationary models make the fine-tuning requirement worse because they require their own extremely precise initial conditions to get started. His alternative proposal, conformal cyclic cosmology, suggests the universe passes through a recurring series of aeons, but this remains speculative and is far from mainstream acceptance. Our universe began in a state of order so precise that chance, by any mathematical definition of the word, is not an explanation. Number 5. The fine-tuning of physical constants. Woven into the fabric of reality are approximately 24 numbers that physicists call fundamental constants. They include the gravitational constant, which governs how strongly masses attract each other, the fine structure constant, which determines how light and matter interact, the strong nuclear force coupling constant, which holds atomic nuclei together, and the cosmological constant, which drives the expansion of space. These numbers cannot be derived from any deeper theory. They are simply measured, written down, and accepted. And when you examine what happens if any one of them changes by even a tiny amount, you discover that the universe immediately becomes sterile, or structureless, or never forms at all. Astronomer Royal Martin Rees cataloged 6 of these critical constants in his 2000 book Just 6 Numbers, demonstrating that the range of values compatible with a complex universe is extraordinarily narrow. If the strong nuclear force were just 2% stronger, hydrogen would not exist, because protons would fuse before stars could form. 2% weaker, and no elements heavier than hydrogen would ever accumulate, leaving the universe as a sparse hydrogen fog forever. Physicist Fred Hoyle made one of the most striking demonstrations of this in 1953, when he predicted that carbon-12 must have a very specific nuclear resonance, a precise energy level that allowed stellar fusion to produce carbon efficiently. He predicted this resonance not from nuclear theory, but because carbon exists, and life is carbon-based. The resonance was found experimentally exactly where he said it would be. Hoyle later wrote that the arrangement looked like a put-up job. The fine structure constant, approximately 1137, governs the strength of electromagnetic interactions. Slight variations would prevent atoms from forming stable structures or prevent stars from burning long enough to produce heavy elements. The ratio of electromagnetic force to gravitational force is fine-tuned to roughly 1 part in 10 to the 40th power. 3 explanations have been proposed. The multiverse suggests all possible values of these constants are tried in different universes, and we live in one where life is possible. A deeper theory might one day show why these values are logically necessary, or the tuning was deliberate, which physics cannot evaluate. None of these 3 explanations has been confirmed. The universe runs on settings, and every single one of them is calibrated precisely and inexplicably for the one outcome that allows anything to exist at all. Number 4. The measurement problem and the participatory universe. In the 1920s, the founders of quantum mechanics discovered something about the nature of reality that has never been satisfactorily resolved, and which the greatest physicists of the 20th century found genuinely disturbing. At the subatomic level, particles do not have definite properties until they are measured. An electron does not have a specific position, or a specific spin, or a specific momentum until the moment of observation forces it to commit to one. Before measurement, it exists in a superposition of all possible states simultaneously. This is not a limitation of our instruments. It is, according to the Copenhagen interpretation formulated by Niels Bohr and Werner Heisenberg between 1925 and 1927, a fundamental feature of reality itself. Princeton physicist John Archibald Wheeler, who coined the term black hole and was one of the most original scientific thinkers of the 20th century, took this seriously in a way that most of his colleagues found uncomfortable. He developed what he called the participatory anthropic principle, the idea that the universe, in some deep sense, requires observers to bring it into concrete existence. In 1978, he proposed the delayed choice experiment, in which the act of observation could retroactively determine the path a photon had taken in the past. This was confirmed experimentally in 2007 by a team at the Australian National University, and the broader reality of quantum entanglement and the measurement problem was cemented by the 2022 Nobel Prize in Physics, awarded to Alain Aspect, John Clauser, and Anton Zeilinger. The measurement problem, the question of what counts as an observation and why observation collapses superposition, has no agreed-upon solution after a century of debate. Many worlds interpretations, pilot wave theories, and relational quantum mechanics each attempt to dissolve it, but each introduces its own deep costs. If reality requires observers, then the universe presents a profound paradox. For nearly 10 billion years after the Big Bang, there were no observers, no minds, no life, no measurement. A universe that requires observation to solidify into definite reality should not have been able to produce the conditions necessary for observers to evolve. The most successful theory in the history of physics quietly implies that reality is not a stage that exists before the audience arrives, and a century of brilliant minds have not reached agreement on what to do with that conclusion. Number 3, the origin of the laws of physics themselves. Every explanation science has ever produced for why the universe behaves the way it does relies, ultimately, on the laws of physics. Conservation of energy, the speed of light, quantum mechanics, general relativity. These laws are the bedrock beneath every bedrock. They are what every why eventually rests on. But here's the question that tends to fall silent in seminar rooms. Why do those laws exist? Why are they mathematical? Why are they these laws, and not entirely different ones? Why are there any laws at all? Stephen Hawking addressed this directly in his final book, Brief Answers to the Big Questions, published in 2018. He asked, what is it that breathes fire into the equations and makes a universe for them to describe? It is a question that sounds almost poetic until you realize it has no scientific answer, and that Hawking, one of the most rigorous physicists alive, was asking it in complete seriousness. MIT physicist Max Tegmark has proposed the mathematical universe hypothesis, the idea that mathematical structures do not merely describe reality, but are reality, and that all self-consistent mathematical structures exist somewhere. Lee Smolin of the Perimeter Institute has proposed cosmological natural selection, in which universes reproduce through black holes with slightly varied laws, and our laws are the product of a cosmic evolutionary process. Neither hypothesis is experimentally testable in any conventional sense. The philosopher David Hume identified a version of this problem in 1739, observing that we cannot prove the laws of nature had to be any particular way. Gottfried Wilhelm Leibniz asked the sharpest form of the question in 1714, why is there something rather than nothing? That question has never received a physical answer, and many physicists privately suspect it never can. Physics explains how the universe works. It has never explained, and may be constitutionally incapable of explaining, why there are rules. Every scientific answer ever produced was built on the laws of physics. But when you reach for the floor beneath every floor, there is nothing there. What is the universe standing on? Number 2. Why there is something rather than nothing. In 1973, physicist Edward Tryon published a short paper in the journal Nature proposing something remarkable, that the universe might have spontaneously arisen from nothing through a quantum fluctuation. His reasoning was elegant. The total energy of the universe, matter energy combined with gravitational potential energy, may sum to exactly zero. If the books balance perfectly, then quantum mechanics allows the universe to borrow its own existence from the void, the same way virtual particles flicker into being from empty space and vanish before the debt comes due. For one brief moment, Tryon's proposal seemed to offer physics a way to answer the oldest question anyone has ever asked. The problem is that a quantum vacuum is not nothing. This is not a philosophical quibble. A quantum vacuum has structure. It has fields, properties, energy, and the laws of quantum mechanics governing its behavior. When Lawrence Krauss argued in his 2012 book, A Universe from Nothing, that quantum field theory explains how the universe arose from nothing, philosopher and physicist David Albert responded in a scathing New York Times review that Krauss had not explained the origin of something from nothing, only the behavior of one particular kind of something. The confirmation of the Higgs field by the Large Hadron Collider in July 2012 reinforced the point. Even the vacuum of space is not empty. It is filled with a field that gives particles their mass, operating according to rules that themselves require explanation. James Hartler and Stephen Hawking proposed their no-boundary model in a 1983 paper in Physical Review D, suggesting that the universe has no beginning in time, in the same way a sphere has no edge. Time itself curves smoothly to nothing at the Big Bang, dissolving the question of what came before. But the no-boundary proposal still requires the laws of quantum gravity to exist and operate. It does not start from true nothingness. No physical model ever constructed has derived the existence of the universe from a starting point that contains no physical assumptions whatsoever. Every origin story physics tells begins with something already in place. Physics can trace the universe back to its first fraction of a second, reconstruct the birth of stars, and predict the death of galaxies billions of years from now. But it cannot take a single step into the void that should have existed instead of all of this, because every tool it possesses disappears the moment it tries. Number 1. The universe is statistically impossible, and the math keeps confirming it. In 2020, the Planck collaboration published its final analysis of the cosmic microwave background in astronomy and astrophysics, the most precise measurement of the universe's large-scale properties ever achieved. The data confirmed the universe's parameters with extraordinary accuracy. it also made the problem worse, because every increase in measurement precision tightens the fine-tuning requirements, and tighter fine-tuning means a smaller slice of possible universes that would look like ours. The universe, examined more carefully than ever before, looked less like a natural outcome and more like a specific selection. Consider what the numbers actually say when you hold them together. The matter-antimatter asymmetry required a 1 in 10 billion imbalance at the moment of creation. The flatness of the universe required a 1 in 10 quadrillion precision in energy density at 1 second after the Big Bang. Roger Penrose's entropy calculation places the probability of our initial conditions at 1 in 10 to the power of 10 to the power of 123. The cosmological constant is fine-tuned to within 1 part in 10 to the 120th power relative to the quantum mechanical prediction. And approximately 24 physical constants are each calibrated independently within narrow ranges that permit complexity to exist. These are not separate problems. They are layers of the same problem, and each layer compounds the others. Physicist Paul Davies, in his 2006 book, The Goldilocks Enigma, described the universe as appearing to know we were coming, a phrase that provoked fierce debate precisely because no one could produce a satisfying mathematical counterargument. Nima Arkani Hamed of the Institute for Advanced Study in Princeton has argued that even the internal structure of the standard model of particle physics is miraculously fine-tuned, independent of any cosmological considerations. Alan Guth, the MIT physicist who invented inflationary theory to solve some of these problems, has acknowledged that inflation, while resolving the flatness and horizon problems, actually makes the overall measure problem worse by expanding the space of possible universes in ways that make our specific universe harder to account for, not easier. The 3 frameworks physicists reach for when confronting this: the multiverse, a deeper unifying theory, and the uncomfortable third option that physics deliberately excludes from its vocabulary, are all either untestable, non-existent, or outside the domain of science entirely. Every tool built to resolve the fine-tuning crisis has sharpened the resolution of the crisis without dissolving it. We are a universe that mathematics says should not exist, inhabited by beings who should not have arisen, governed by laws that have no origin, shaped by constants that have no derivation, having evolved the precise capacity to measure our own impossibility with instruments that confirm it more precisely with every passing year, and we have not yet found a single equation that explains why we are here to notice any of it. If you want to see more videos like this, click the video on screen now and make sure to subscribe.